Yeah, so this webinar series is mainly going to focus on how to use BOSpulse to do a pulsation analysis. We're also quickly going to show isotracer. Yeah, but we're mainly going to use BOSpulse. And like I said, this is a series of 3 events. So this first one taking place today is going to focus on how to set up your acoustic model, how to use the different interfaces that BOSpulse has, yeah, to set up your pulsation model quickly. Then the second session, which is going to be in 2 weeks at the same time, is actually going to set up the API analysis and do your pulsation analysis, look at the pulsations and apply some mitigation strategies for those pulsations. And then in the last session, which is going to be in 4 weeks from now, we're also going to look at how to set up a structural model and mitigate vibrations as a result of pulsations that you might have. So that's a bit of the outline. And then when you look at a pulsation analysis, you can schematically show it like this. So here, the different boxes represent different aspects of the pulsation analysis, and the upper side is actually for the flow analysis, and the bottom side is for the structural analysis. So for the flow analysis, you're going to have some kind of equipment. So typically a positive displacement equipment like a reciprocating pump or compressor. And that's going to introduce acoustic excitations into your system. And that equipment is attached to some model geometry. So your piping, maybe you have some heat exchanger, some knockout drums, you name it. And those together can lead to pulsations. And these pulsations don't necessarily cause problems, but a result of these pulsations is that you're going to have pressure differences in your system. So you might have 2 elbows in your system where you have a pressure difference, and as a result, there will be an unbalanced force on that section between those 2 elbows. And that's what we call shaking forces. And so when you look at the structural part of this overview, the shaking forces are going to be the excitation source. From a structural point of view, you're again going to have some model geometry and some supporting of your system. And again, together, these can lead to vibrations and subsequently to failures. And so that's something we want to prevent. And this picture is going to help us identify where we can actually have some mitigations. And if you look at the right-hand side, here on the x-axis, there's the frequency that you're looking at. And so your equipment will typically induce some excitations at multiples of the driving frequency of your equipment. So for instance, at 1 times the driving frequency, 2 times, we call these harmonics, 3 times. And then your model geometry is going to have inherently some acoustic modes. And these are modes where, for instance, you can expect standing waves between some points in your system. And those can interact with each other. So the acoustic excitation can couple with some of these acoustic natural modes if they're close in frequency, and that will lead to an acoustic response. So if there is not much overlap between your acoustic excitation and your acoustical modes, you're also not expecting that much of an acoustic response. Whereas if there's quite a bit of overlap, those might couple very well and your acoustic response will be quite big. And the same goes actually for your structural model. So if you have a structural excitation at some frequency that couples quite well with a structural mode, you're also going to have a large structural response. And so in this particular session, we're going to focus on the upper 2 boxes. So we're going to look at the equipment, how to model that. And in this case, we're going to import it from the aerial compressor configuration performance program. We're going to look at how to model a gas passage from an aerial schematic. We're going to model some interstage piping using our tool isotracer, and we're going to model some discharge piping using a PCF interface. It's gonna be quite hands-on, and I'm gonna do it live. So please forgive me if it's not going as smooth as desirable. Yeah, and so if we look at the starting point of our pulsation analysis, we're gonna start with modeling this equipment over here. We're gonna start with an aerial compressor, but this applies to other types of compressors as well. We currently have an interface with the aerial performance program, so it's possible to import some settings from that performance program, but in the future we're planning to extend this to other types of compressors as well. And so if you look at this particular model over here, you see a 6-throw compressor. So these are the 6 throws. You have a crankshaft over here, which is driving the compressor, and you have some pistons that are going back and forth in some volumes over here. So here you see a schematic of this of one of these throws. You see again the crankshaft over here again, and a piston that's moving back and forth. And as a result, there are some volumes over here and over here. This is the crank end, this is the head end. And these volumes are changing over time, driving some check valves that are located over here and here to open and close appropriately. And as a result, you can compress the gas and exhaust gas at a higher pressure into your discharge piping. We actually have a pretty extensive course on engineering trainer into the theory of reciprocating equipment. But this is as far as I'm going to go into it for this particular webinar. So the starting point of our pulsation analysis is going to be an aerial performance run. This is the aerial software. I'm not going to dive too deep into it. One of the takeaways is that in this case, we're going to have 2 stages. So we're going to increase the pressure in the first stage and then increase it even further in the second stage, which you can see over here. We have a couple of operating cases over here. So we have 4 operating cases. And in these operating cases, what we're doing is we're changing the gas type that we're looking at, and we're changing the discharge pressure. And we let Ariel make a suggestion for a compressor configuration. So this is the compressor configuration that Ariel came up with. It's a 4-throw compressor that's gonna increase the gas pressure in 2 stages. And so what you can do in Ariel is you can export this compressor configuration to a XML file, like the one over here, store it somewhere on your computer, and then go to BOSpulse. And this is BOSpulse. So for people that aren't familiar with the software, this is what it looks like. So on the right hand side, we're going to build up the model, and on the left hand side is where we do our operations on the model. And actually in all our software packages, we have a tab-based workflow. So we work from the left to the right here. So we start in the model tab and work our way onto the results tab. What you can do in BOSpulse is just start modeling like this. So for people that are familiar with, for instance, Caesar, this is a typical workflow. But typically you would have some of your data already available in some other kinds of formats. It's possible to start building your reciprocating compressor cylinders like this, but it's way more convenient to use our interface with Ariel and import it from there. So if we go to tools and then assemblies, you can see that we have a dedicated aerial compressor type over here. So we're going to add one. We're going to browse to that file that we just exported from the aerial compressor interface. Import that, give it some name. And so this is what's being imported to BOSpulse. So it looks a little bit different than what you're seeing in the aerial compressor program. And what we actually import, if I go back to my presentation, are these volumes that are changing, because these are actually important for your pulsation analysis. And so for each throw, we have a crank end and a head end. You can see that over here. So the operating mode for the outer one is set to the head end, to the inner one is set to the crank end. So that's being imported. We also import a lot of the geometric properties of such a cylinder. So we import the piston diameter, rod diameter, crank arm radius, and so on. We import clearance volume, so you don't have to fill that out by yourself. And what we also import, and then we go to the next step, are the operating cases. So in BOSpulse, we have something called scenarios. And scenarios are variations with respect to your base model. So in the scenarios, you can say, okay, I have my base model, but I want to look at some different temperature now, or I want to look at different discharge pressure now. Actually, any parameter you see over here, you can change in the scenarios, and then compare within the same model their impact. So because we had 4 operating cases in the aerial performance program, we also have 4 operating cases in BOSpulse. And in these operating cases, you can see that some square blue boxes have popped up. And these are the flow boundary conditions that have been imported from the aerial performance program. So we applied fixed pressure boundary conditions here that are based on the calculation that was done in aerial itself. And something else that we imported from aerial is a fluid type. So you can see here this compressor has been assigned the fluid type aerial gas number 1. And if we were to go to our database, which is located under Tools, Database, and then go to the fluid section, you can see that actually a couple of gases have been imported from this aerial configuration file. And if I click on one of them, you can see that the gas composition has already been populated for you. So this interface saves you quite a bit of work when setting up your model and starting doing your pulsation analysis. So this is going to be the starting point of the pulsation analysis. We now need to connect these cylinders up, because the model like this we can't really do an analysis on. So the next step that we're going to do is we're going to look at how to model a so-called gas passage. And a gas passage is there's a sort of volume here, sort of a 3D complex shape around the piston and the cylinder chambers, where the gas is flowing into from the chamber and then out of the compressor itself. And this is quite a complex 3D shape. And in BOSpulse, we're dealing with a 1D model. So there needs to be some mapping of that 3D shape to a 1D model in BOSpulse. And luckily, Aerial gives you already some guidance on how to do this. So if I open up the performance program again, if you click on one of these rows and go to the gas passage data, Aerial gives you some suggestion on how to model this as a 1D model. And so this corresponds to, I think, the crank end, and this corresponds to the head end. But as you can see, there are actually 2 sides for each cylinder that's below here. And that's because, well, for this particular throw, there are two check valves. And in BOSpulse, we only have one single node to connect to. So that's a bit of a problem. And the way we typically deal with that is we try to aggregate. So part A and part B, we keep the same, but we try to aggregate this part and this part together. And then, yeah, typically we end up with a model like this over here. So there we change the effective diameter of C and D, so that the effective area, flow area, is kept the same, and also the acoustic length in the gas passage is the same. And let me pull up the model itself. So here we have that model. And one of the things that we typically also do is we set the acoustic length, which is a parameter over here. So we override this, because if you don't do that, BOSpulse might identify this part over here as a T-junction and try to reduce some acoustic length here. And we don't want that. So we want to keep it the same as the schematic as Ariel. Yeah, so it's good practice to, for this gas passage, override the acoustic length everywhere, so you're making sure that the acoustic length is actually correct. So let's go back to our main model and try to, so this gas passage has been stored to a separate BOSpulse file. You can actually make a database if you want with gas passages, because they typically don't vary that much, and then import from that into your main model. So BOSpulse has support for importing various types of other formats. So it can import other BOSpulse files. It can also import from Caesar. It can import from PCF files, and so on. Let's browse to that gas passage. And then instead of replacing the model, we want to extend it. And we want to merge nodes. And you can see over here now, this is connected automatically to these compressor cylinders. You can also see that the compressor cylinders are a bit oversized in this case. There's no data in the Ariel compressor interface about the actual size of these cylinders, so the way they are imported is a little bit random, and it's actually only used for visualization purposes. So in this case, I'm gonna decrease them a little bit. We need to do this for all the gas passages, so both the suction side as the discharge side. I'm not going to do that for each one separately, but I prepared a model already where I did this. So here we ended up with a model where all the gas passages have been modeled, connected to our compressor cylinders. You might notice that on the suction side of the first stage, I didn't add a gas passage, because we're gonna neglect everything that's happening on the suction side. So we're cutting off the model over here. And then what's the next thing to do is connect the first stage to the second stage. So these throws, they form the first stage. These ones form the second stage, and we're gonna connect them up. And in this example, we have isometrics for the interstage piping. So we're going to use our tool IsoTracer to model that interstage piping. And you can select your own unit set. So we support metric and use as customary. You can also make your own ones. And our isometrics are going to be in metric units. So that's why I picked that one. So this is our tool IsoTracer. You can see again that we have a left to right workflow over here. And what you can do in IsoTracer is you can load up isometrics. Let's give them a name. And let's remove the default one. And so this is actually going to form the cold side of the interstage. And this one is going to form the hot side. So let's rename it. And then in IsoTracer, what you can do is you can go to the markup page and start tracing this isometric. So if I hit this button, I can start tracing. There's also a lot of shortcuts in IsoTracer to make your workflow even faster. So if I hit T, I can also start tracing. And let's start tracing over here. So if I hit this node over here, I can start tracing. I need to give it a base number, and I need to give it some schedule. So all of our packages have a built-in database of pipe schedules, and in this case, we're going to look at the standard number 3. So if I hit 3 here, IsoTracer and also BOSFluids and BOSPulse, our packages, they automatically convert that into the proper diameter and thickness. And so now I'm ready to start tracing. So now if I hit to the next point over here, you can see on the right hand side that my model was being built, and on the left hand I need to fill out the length that's associated with this one, and this way I can completely model my isometric. So let's do this part over here. Let's go around the corner, and you can see on the right hand side that bends are automatically added. So let's do this part as well. And by hitting the right mouse click, you can stop tracing. So now we model this part. Well, let's model a little bit further over here. Let's continue this trace. Like that, and let's do one final bit. So we have a couple of heat exchangers over here, and the isometrics, they continue on onto the other isometric. So let's start here again, 50. And now if I want to continue, I just simply click on the other isometric. I hit where I need to continue, and I make this final part here and stop tracing. And if I go back to the other one, it's pretty easy to, for instance, mark this one as, in this case, an equipment. We're going to make it into a proper heat exchanger in BOSPulse itself. But you can see this is a way to pretty quickly build up your models. And so IsoTracer comes, if you have a BOSFluids or a BOSPulse license, it comes free with that. And it's also available as a separate tool. And let me open up a model where I completed all this piping. So I ended up with this model over here. And this can be exported to various formats. So you can import again to Caesar files. You can export it to BOSFluids and BOSPulse. So in this case, we're going to export it to a BOSPulse file. And then go back to our main model and import it here. And again, extend the model. There we go. So now we need to connect this up with the rest of our compressor cylinders. So let's start here, and this needs to be, we need to make sure that we make the node numbering the same so it connects up. So if I click on this one, I need to replace this one with that node number. And you can see now that it's appropriately connected up with this gas passage. I need to do that for all of my nodes. So let's quickly do that. And also for the second stage. It's a bit tedious, but if you get the hang of it, it's pretty quick. So there we go. So now we modeled the interstage piping, but we need to make some changes. And like I said, these are heat exchangers, so we need to make this into proper heat exchanger elements. So in BOSPulse, you have a set of different element types to choose from. So you have some piping related element types like reducers and pipes. We have some equipment like reciprocating compressor and pumps. And here we find the heat exchanger. So let's make it a heat exchanger. This is gonna be 0.4, 0.04, and it's gonna have 14 tubes in it. Well, you can model the tube side in BOSpulse, but you can also model the shell side. And what this element type does, it calculates the appropriate flow resistance, so the appropriate pressure drop that we're gonna expect in our system. There are some other changes that we have to make because, as I mentioned, we imported pressure boundary conditions on both sides of our cylinders. But because we model the interstage piping now, we actually are not gonna need these ones here anymore, because BOSpulse is gonna automatically determine what the pressure is gonna be in all this interstage piping. So these can be removed. You can select all of them at once by using the control button. And we want to actually erase them for all the operating cases. So if you click them all together and then mark this flow boundary condition as not specified, these flow boundary conditions are removed. Some other things that we need to change, and I want to point out a tool that we have under here, under the eye icon, which is the model verification tool. So if I show the fields, we can actually visualize any model parameter here in the 3D viewer as colors. And one of the things that we need to fix is the gas that's flowing through our interstage piping, because if I show the field now, you can see that for the compressor cylinders, the gas has been defined, but for all the interstage piping and for the gas passages, yeah, this is still not specified. So if I go to case number 1 and then to my elements and select all of them, I can make sure that this has the appropriate gas. I can do this for all of them, but I'll show you later on how to do it in an even easier way. And something else that we need to change is the temperature, because the temperature is now at a default value. But looking at one of the compressor cylinders, you can see that there is a suction temperature and discharge temperature. This is again populated from the import from the XML file from Arial. And so we need to make sure that the proper discharge temperature is set here and the proper suction temperature up to this point. And for that, we're gonna use a built-in tool within BOSpulse, which are element and node groups. And actually, I'm first gonna break these two heat exchangers, because we're gonna let the temperature drop take place halfway the heat exchanger. So let's break these elements first. There we go. Yeah, so in BOSpulse we have a concept of element groups. You can see there are some element groups that are associated with the properties of elements themselves. So you have a group based on the type. You can also make groups based on any parameter. So if I'm interested in a group based on the outer diameter, that's possible as well. So these are conveniently grouped then. But you can also make custom element groups. And so there was already automatically generated one element group for all our compressor elements. And actually all of the interstage piping was added to a group as well. So let's maybe rename that one. And in order to do operations faster, it's convenient to make some more element groups. So maybe let's add all the hot interstage piping to a separate group. And if you double click on the line here, this actually corresponds to the tracing that we did in IsoTracer. So if I double click on this line, this trace that we did in IsoTracer is all selected. So this is an easy way to select some parts of the system. So I want to add this to a group and maybe also include the gas passage as well, because we want to adjust that the temperature there as well. Let's add this too. And then let's make a new group. Call this interstage hot. And then add all these selected elements to that particular group. Now we could possibly do the same for the cold side of the interstage piping. So now if I go back to the compressor cylinder over here, we want to assign this discharge temperature to all of that interstage hot piping. So by double clicking here on that group, all the elements are selected together and I can specify the temperature for that part. Again, I could do the same for all of these operating cases, but there's a bit of a more convenient way to do that, because under this button or under tool scenarios, we have a what we call a scenario manager. And in this scenario manager, we show in the rows, we show the different cases that have been created. And in the columns, we show parameters that are varied across these operating cases. And so if I click on one of these columns, I can also see in a model viewer which elements are associated with this column. So if I click this one, I'll see this is associated with all the cylinders. And if I click this one, I can see that this is actually associated with all the interstage piping, where I just specify this gas. And actually what I want to do is make sure that the fluid for all of this interstage piping is equal to the fluid of the compressor. So you can also make your changes in this table over here. So make sure that everywhere the same gas is used. And then when we look at the temperature, you can see here, this is the column associated with the temperature that we just specified. And this column should actually be the same as the column associated with the discharge temperature of these compressor cylinders over here. So that's either this column, it's this one. So I need to make sure that this column is properly copied to the one over here. So that's also quite a quick way to set up your scenarios and make sure that everything is filled out correctly. Again, I'm not going to do everything manually because that would get kind of boring, but I already have a model where I did all this. And so then we're basically left with this model, and we need to do one more thing. We're going to model the discharge piping of the second stage. And for that, we have PCF files. So there is an interface in BOSpulse to import PCF files. I'm going to browse again to the PCF file itself, extend the model. Not going to merge the elements, and the rest I'm going to leave at the defaults. These are the pipe schedules that BOSpulse has read from the PCF file. It's possible to override this, but we're going to leave it at the default because this seems fine. And there we go. There we have the interstage piping, which we again need to connect up. So I'm going to have to make sure those node numbers match up again. Okay, that was the wrong order. Like that. And this one seems connected now, but it isn't because the node numbers are still different. So I'm gonna have to make sure that they are connected up again as well. And by the way, over here you can toggle any node labels and element labels. So again, we need to, well, we are left with some pressure boundary conditions over here, but they're in the middle of our model, and so they need to be removed. And we actually need to specify a pressure boundary condition over here. So what I can do is I can go to this node and boundary condition here, and when I hit Control C, go to this node, hit Control V, the properties are copied. You can also do it by right mouse clicking and pasting it. And so now we have moved our fixed boundary condition from here to here. I need to remove them here still. And so this is the point where we're going to cut off the model. And we have a couple of knockout drums over here, and these are going to remove some excess water vapor. And because of the large volume, we are expecting that any pressure pulsations that are coming of our equipment over here are going to be attenuated by these knockout drums. So we're not expecting that much pulsations in this piping over here, and we're actually going to see that later on in the sessions. And this is actually tapping into some other piping, but we're just cutting it off here. And because this is tapping into other kinds of piping, it's not really appropriate to use a fixed pressure boundary condition over here, because a fixed pressure boundary condition is really meant for something that has a fixed pressure, like maybe a big tank where the pressure is constant. And a fixed pressure boundary condition is going to result in pressure waves reflecting off of it. And in this case, we don't want that, because the pressure waves are going to continue into the continuous piping over here. So it's more appropriate here to use an anechoic boundary condition, which is the long pipe in BOSpulse. So we're going to specify it like this. We're going to make some final touches to the model. So we're going to add some valves at these locations. So that's also a particular element type in BOSpulse. We're going to need to specify a discharge coefficient for these valves to appropriately calculate the pressure drop across these valves. Let's set this to a typical value of 0.4. We're going to make sure that these are capped off. So we have a cap type for that. We're going to make that flat. And again, like for the interstage piping over here, we actually also need to set the appropriate fluid and the appropriate temperature for this discharge piping over here, which I'm not going to do live, but that is typically something that's necessary to do. And then so we would end up with a model like this. So this model is actually ready to do a pulsation analysis on. I'm gonna save that for the next session. I am though gonna do a steady state analysis. So we're moving on to the next step here, and we're gonna set up a steady state analysis. We're gonna use a base frequency of 1800 hertz, 1800 RPM, and you can actually do some math in all these fields where you can specify numerical values. So it's gonna be 1800 hertz. RPM, and to convert that to hertz, we need to divide by 60. And one other thing I'm gonna do is I'm gonna go to my reciprocating compressors, and you can see that this operating speed has also been imported from the aerial interface, but I'm actually gonna leave this blank. And what this does, it's gonna say, okay, take the one from the analysis instead of specifying it here directly, which is going to be convenient when you want to perform a parameter schedule or something like that. So I'm going to need some more iterations here, because we're solving the interstage pressure as well. So the steady state solver might need some more steps to converge. And then when I move to the run tab, I can combine this analysis that I just defined with the operating cases that we specified and run all of them. We have pretty fast solvers, so you can see that all 6 operating cases have now been solved already. And if I go to the results tab, I can inspect the steady state solution that BOSpulse found. So here you see the pressure distribution that BOSpulse determined. So you can see it starts at a suction temperature at the first stage of 29 psi. That pressure is being increased by the first stage to a value of about 67. By the way, by clicking your right on the right hand with the right hand mouse button, you can display the numerical value associated with the colors in your model. The pressure decreases a little bit due to the friction of the heat exchanger, and then it taps into the second stage over here, where the pressure is increased again to the second stage, and then taps into all the discharge lining over here. I always like to look at the profile plot graph. So if I click that one and I click a node over here and a node over here, I can see actually this data set as a function of the distance across this path. So here in this profile plot, you can see again the pressure being increased in the first stage, then decreasing a bit because of the friction of the heat exchanger, increasing again in the second stage, and then tapping into the discharge cutoff over here. And so BOSpulse determined the pressure and also the flow rates in your system, so you can inspect that as well. So by right mouse clicking again, you can see the flow rate that BOSpulse found. And so basically we have a model now that's ready for doing a pulsation analysis on. That is going to be part of the next session of this webinar series. We did receive some questions beforehand, and I made a selection of a couple of those. Most of them were about pulsation analysis, so I'm going to save some of the questions to the next session, but yeah, let's go into some of the questions I selected. So one of the questions was, how can you deal with multiple valves on the compressor head end or crank end cylinder? And so this very much touches on the modeling of the gas passage, where we also simplify the model so that it only connects to a single node of the compressor cylinder, even though you can see there are multiple connections over here. And so if there are multiple valves on one side of a compressor cylinder, you can do something similar and aggregate the properties of the valves onto a single valve. And we haven't really looked at the valve properties of this cylinder, but one of the fields of the compressor cylinder are actually the valves. So we left them at ideal over here, which means that they're going to be open when there's a positive pressure difference and going to be closed instantaneously if there's a negative pressure difference. But we also have some more sophisticated valve models. So if you go to the simulated one, you can actually fill out the properties of the particular valve, and BOSpulse will do the mechanics of the valve opening as a function of the pressure difference between the cylinder and the suction or discharge side. So if you have multiple valves, you need to aggregate the properties of those valves onto a single valve. So you need to increase, if you have two valves, for instance, you need to increase the valve diameter by the square root of 2. And that way you can capture the behavior of two valves, but actually map to a single valve. One other question was, how can pulsations in a reciprocating pump system be modeled using the BOSpulse software? Yeah, so pulsations in reciprocating pump systems can be modeled in a very similar way as we did for our reciprocating compressor, except instead of specifying a reciprocating compressor, you would specify a reciprocating pump, and you wouldn't use a gas, but you would use a liquid. And another difference is that, for instance, for the to calculate the increase of the pressure in the cylinder for a reciprocating compressor, we use a polytropic exponent, and for a reciprocating pump, we use a fluid bulk modulus. But other than that, it's very, very similar in BOSpulse. So the next question is how to set up a piping model with a positive displacement pump. So for example, a rotary lobe to determine the magnitude frequency of pulsations. So there is no dedicated element type for other types of displacement pumps, such as rotary lobe or screw compressor pumps in BOSpulse. However, the way they work are very similar because there is a volume that changes in size and that opens and closes to the suction and discharge side. And for these types of compressors, the manufacturers are typically not so generous providing the actual geometric information and how the volume changes and how the opening changes. But it's still possible to model a positive displacement equipment like this in BOSpulse. And so I have an example model over here where we modeled a rotary lobe blower, which is over here. So here is the suction side. And instead of modeling this as an element, we applied a flow boundary condition over here. So what you can do is you can specify a flow boundary condition of type periodic flow. And we determined what the flow rate coming into that reciprocating equipment would be. And that would look like this for this particular case. And so this flow profile is imposed on the system, and as a result, you're able to determine the pulsations and the magnitude of the pulsations in BOSpulse. Another question was how to obtain the speed of sound of the fluid in BOSpulse. I must admit that's a little bit hidden in BOSpulse, but if you go to the analysis, there's an output data section over here. If you double click that, these are the data sets that are being generated for this particular analysis. Most of them are enabled by default, but we also have two over here that are disabled. And if you enable them, they will also be shown in the output. So let's do that. Run again. And then you'll see that you have two additional data sets that are being shown. If you click on them, you can actually inspect the wave speed that was used by BOSpulse throughout the model in the 3D viewer or in your graph section over here. And then the last question, how to verify the suction, discharge piping layout, valve details, and process conditions used in a model to reflect the actual plan design. Yeah, so there are various ways to answer this question, I think. So BOSpulse has some integrated features, as I showed, to do some model verification to actually using this eye icon over here to make sure that you didn't make any modeling mistakes. But other than preventing modeling mistakes, you can also use the result of the steady state analysis in BOSpulse to verify that the model actually gives similar results to measurements of, for instance, the pressure and the flow rate. That is provided that those measurements or that data is actually available. Yeah, but even if you prevent modeling mistakes and make sure that your steady state results match measurements, the honest answer is that you're never going to be able to model reality 100% accurately in BOSpulse or any other software package for that matter, because there will inherently be modeling inaccuracies and uncertainties. For instance, you're mapping reality, which is three-dimensional, onto a one-dimensional model. And likewise, there will be uncertainties in the properties of your model. For example, the actual composition of your gas might deviate a little bit from the values provided. So basically, you're inherently gonna have deviations from reality, and there are built-in ways to deal with that in BOSpulse, and we're actually gonna show some of that in the next session. Yeah, so I hope to see most of you in the next session where we're gonna go into the modeling of the or doing the actual pulsation analysis and apply some mitigation strategies to mitigate pulsations. Yeah, so I'm hoping to see you in 2 weeks.